Hi, thanks for joining me. Today I'm going to be doing something I've never done on the channel before, and that's a bit of mechanics slash dynamics. We've got a basketball here, and we're going to throw it at some angle theta from the ground. So the ground is here, we're throwing the ball from the ground at some angle upwards theta, and we want to throw it as far horizontally as possible. So in other words, we want to maximise this distance here, from here to here. We want to know at what angle theta must we throw the ball at to maximise this distance here. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so what I've done is I've drawn an XY plane like so and placed the ball at the origin, and here's the trajectory of the ball, and here's the initial direction in which we throw it in, and here's the angle theta. And I've labelled the point R when it hits the ground again, because that's the distance we're kind of measuring, and we want to maximise R by varying theta. The first thing we're going to do is get some equations involving r and theta, and the way we're going to get those is using the suvat equations. If you've not seen suvat before, it just sort of comes from Newton's law that F equals ma, and then you sort of integrate to get some of the suvat equations. In this video I'm not going to be proving them slash deriving them, I'm just going to be stating them and then using them to work out what the maximum value of r is. Okay, so firstly what we're going to do is sort of resolve horizontally. So we're going to resolve this way. And let's write down what each of the SUVAT are. And let me just quickly go over what they are if you've not seen them before. Firstly, we're going to be considering the ball when it gets to this point here. So when the ball is here, S is the displacement, U is the sort of initial velocity, so the velocity here, V is the final velocity, A is the acceleration, and T is the time it takes to get here. Okay, so what is its horizontal displacement, S, when it's here? Well, it's clearly just R, because it goes R across, like so. So its horizontal displacement is r. Its initial velocity, well, we haven't actually given it an initial speed yet, so let's just suppose we give it initial speed capital A. It doesn't really matter what it is, but suppose we give it initial speed capital A. But then of course that means it's got some velocity in that direction and some in that direction, and the velocity it has in the horizontal direction, if we kind of draw a triangle it might make more sense, like so. This here is just A cos theta, and this here is A sine theta, like so. So its horizontal velocity is just A cosine theta, or its initial velocity, A cosine theta. V, we don't actually care about. Its final velocity we don't care about for this problem, so we're going to leave it blank. A is its horizontal acceleration. Now for this problem we're going to just assume there's no air resistance, because obviously if you take that into account this makes it a more complex problem, but for this sort of solution we're going to assume no air resistance. So its horizontal acceleration then is 0, because there's no forces acting on it once you've sort of thrown the ball, that's it. It's just the only force acting on it is gravity, but that acts sort of vertically as opposed to horizontally. There's no horizontal forces acting on it. So acceleration is actually just 0. And the time it takes to get here, well, we're just going to call that capital T. We don't know what it is, but we're going to call it capital T. Okay, now we can use one of the suvat equations, which is S equals ut plus a half at squared. Just plugging in these numbers here, we get r equals a cos theta times capital T, and then this half at squared term vanishes because a is 0. So we've got one equation involving r, theta and t. This equation here, r equals a cos theta t. Now what we're going to do is resolve vertically to get another equation, and then we can start doing some algebra. Okay, so we just derived that r equals a cos theta t. Now we're going to resolve vertically to get another equation. So we're resolving vertically, and I'm going to say let down be the positive direction. It doesn't really matter which let be the positive direction, but I'm going to let down be the positive direction because that's the way gravity acts. Okay, so again we're going to write S, U, V, A and T, like we did before, and again we're considering the ball when it's here, so it's gone all the way here. So S, what is its vertical displacement? Well, its vertical displacement is 0, because you can see the y coordinate here, from here to here, doesn't actually change. It doesn't really, its net up and down movement is 0. Of course it does go up a bit, but then it goes back down to the same y coordinate. So S is actually 0. What is U? Well, U is its initial vertical velocity, and remember we said that's A sine theta, but that's A sine theta in the up direction. But of course we're letting down be the positive direction, so in fact the initial velocity is kind of minus, so minus a sine theta. like so. V, again, we don't care about what V is, so we're going to leave that blank. A now is the acceleration downwards, and that's G, so the constant, the gravity constant, 9.81 something. It doesn't actually matter what G is, as we'll see at the end. It's just a constant. Well, in fact, it is just a constant, but it doesn't really matter what it is. But G is just the sort of force due to gravity, the gravitational constant. Okay, and what is T? Well, T is still the capital T we had before. The time it takes to get there is still going to be the same, regardless of whether resolving horizontally or vertically. And again, we've got S, U, A, and T, so we're going to use S equals UT plus a half AT squared. So let me just write that first. S equals UT plus a half AT squared. Plugging in everything, S equals 0, U equals minus A sine theta, T, and then plus a half GT squared. Now, one thing we can do straight away is divide through by capital T. We know capital T is non-zero because it doesn't get from here to here in 0 time. It must take some positive time. T is strictly greater than 0. So we can divide through by T and then bring this A sine theta onto this side to give us that A sine theta is equal to a half GT, like so. Okay, now we've got this equation here, this equation here. Let's do some algebra and see if we can work out the maximum value for R. Okay, so now we have these two equations involving R, theta, and T. What we're going to do is take this second equation here and just multiply both sides by A cos theta. So the left-hand side then becomes A squared sine theta cos theta. And that equals a half GTA cos theta, like so. Now, from the first equation, T times A times cos theta, this guy here, is just R. So we can simplify this right-hand side to just a half GR. And this left-hand side is A squared sine theta cos theta, but we can use our double angle formula that sine 2 theta equals 2 sine theta cosine theta to write this thing here as a half A squared sine 2 theta, like so. Now, of course, we can cancel the halves from both sides and then divide both sides by G to give us that R is equal to A squared over G times sine 2 theta. Like so. So now we've got an explicit equation for R involving theta and these constants here. We don't really need to worry too much about A and G. This is just some positive real number depending on what A is. So sine of 2 theta then, we want to maximize the value of R, and that's going to be precisely when sine of 2 theta is 1. In other words, when theta is 45 degrees. Because remember, theta from the diagram is between 0 and 90 degrees. So to maximize R, that implies that theta equals 45 degrees, or pi over 4, whichever you prefer. And of course, then we can see that R is going to be just A squared over G. So that means if you're throwing a fixed speed and you want to make it go the furthest horizontally, if you ignore air resistance, you want to throw it at a 45 degree angle. So for example, if you've got one of those tennis ball shooting machine things and you want to get it as far as possible, you'd throw it at 45, or you'd angle it at 45 degrees, which I think is pretty cool. But obviously you can make it go further by increasing your initial speed. But if that's fixed, then the best way to get it as far as possible is to throw it at 45 degrees. Anyway, I hope you have enjoyed this mechanics dynamics kind of video. If you want to see more mechanics dynamics, I'll be more than happy to do so, although it's certainly not my strong point, but perhaps I can find something that even I can understand, and then I'll share it. But I hope you have enjoyed this video. Thanks for watching. I'll catch you in the next one. Have a great day.